Welcome back. In this chapter, we'll be looking at some counting problems, and to do so, we're going to express our counting problems in terms of sets. So that's where we're going to begin by first looking at some basic ideas in set theory. A set is any collection that we might have of objects, and the things that are inside the set, we call those elements. So as an example, I might be interested in the first three positive numbers, counting numbers, 1, 2, and 3. And so as a set, I could write them as 1, 2, and 3 inside of curly brackets. That's the notation that we use for sets. If we wanted to list all of the elements in a set, we'll list them inside of those curly brackets. And whenever you see curly brackets in this course, that's going to be some kind of a set. We could put anything in. When I said a set is a collection of objects, sometimes those objects might be numbers, it could be people's names. So as an example, if we're thinking about the set of people who are teaching Stat 216 at Camosun, there's only two people doing that, Susan and Bree. So the set of all the Stat 216 instructors would be Susan Chen and Bree Wilton. The only restriction that we have when we're talking about sets is that we should list things only once. So there are no duplicates inside of a set. Some other things that we might want to think about would be if we're interested in more than one set, it might be nice to be able to refer to it. And to do that, we usually name our sets. And we're going to give them a capital letter name. So I might say, here are the three largest cities in Canada, Vancouver, Montreal, and Toronto. And if I wanted to think about that as a set of largest cities, I could call that set A. And then I'd write set A is equal to the set that contains Vancouver, Montreal, and Toronto. Just as a little fact, for sets, it really doesn't matter what order we list things in. So if you'd said Toronto, Montreal, Vancouver, that would have been the same set. They would have been just as equal as the original set. The other thing as well, that a lot of times when we're thinking about sets, the reason why we want to name them is because maybe they're too big for us to list everything that's inside. If you're thinking about all the numbers between 1 and a million, and you wanted to think about that as a collection of numbers, as a set, you'd have to write a million things down, and that would be really unpleasant. So instead, you might say, let B be the set of whole numbers between 1 and a million. And then instead of me having to actually list all those numbers, it's now just understood that 73 will be inside of set B, and so will 592 and any other number that's between 1 and a million. So here's a couple of sets I've defined. All the even integers, so those are whole numbers, positive or negative or zero, that happen to be even. That's definitely an infinitely large set, and so there'd be no way for us to list all of those elements. If we're thinking about the set of all the cities and towns in Canada, that's a finite set, but probably way too big for me to want to list them. I mean, if it was just cities, maybe we could get away with listing them. But if we say cities and towns, there's definitely going to be hundreds, if not thousands. So I would probably just define it as the set B rather than trying to list everything inside of it. If I had a third set, set C, all the classrooms in the Young building, that's a relatively small set, so definitely finite and small enough that if I wanted to, I could list everything. A couple of little bits of notation to throw in. Sometimes we might want to talk about whether a particular element is inside of a set or not, and we have two little symbols here to use. The first one, which sort of looks like a funny letter E, it's the Greek letter epsilon, and we use this one to refer to something being an element of a set. And to say that something is not an element of a set, we just put a little slash through that epsilon. So if I were thinking about A, the set of all the even integers, 6 definitely is one of them. So I could say that 6 is an element of A. So that's what I would write, 6 with that little epsilon A. And I would read that, 6 is an element of A. 7 is not an even integer, so I would say 7 is not an element of A. I would write that, 7 is not an element, so epsilon with a slash through it and A. We also might have two sets where maybe there's a relationship between them, where everything that's inside of one set happens to also be inside the other one. So that sort of a relationship is called a subset relationship. When we say a subset, it's a set that's inside of another one. So for example, if I'm thinking about all of the Camosun students, that would be a set. And then if I'm thinking about the Camosun students who are taking Math 109, that would be a subset. That's a set that's inside of that bigger set. If that's the case, if A is inside of B, then I would write A is a subset of B using this notation. You'll notice that the subset notation looks very similar to the less than or equals to symbol that we use for numbers. And it's a similar sort of an idea. If A was a subset of B, then A could not possibly have more things in it than B does, because everybody that's inside of A would have to be inside of B, and maybe B would have some extra things on top of it. All right, time for an example. Let's get going here with these three sets, A, B, and C, and we just want to know which of these statements happen to be true, which are false. So just some practicing with our new notation. The first one is asking us, 3 is an element of B. So is that a true statement or not? I'll need to look at set B and ask myself, is 3 an element of that? And it is not. So if 3 was an element of B, that would certainly not be true. That's a false statement. 2 is not an element of C. For part B, I would ask myself, is that true? I'm looking at C and asking myself, is 2 not inside this set? And definitely for C, 2 is not inside that set. So yes, if you said 2 is not an element of C, that would be a very true statement. All right, the next four are all about subsets. So when we say A is a subset of B, we're saying that everything that's inside of A is also inside of B. So now I need to ask myself, A has a 1 and a 2 and a 3 inside it. Are all of those things inside of B? Does B have a 1 and a 2 and a 3 inside of it? The answer is no. There's some things in A that are not inside of B, so this would be false. A is not a subset of B. The reverse, though, is B a subset of A? Is the set B contained inside of set A? Set B has two things in it, 1 and 2, and both of those things happen to be inside of A. So yes, B is a subset of A. We would say that that's a true statement. Two last ones. C is a subset of A. C has a 1 and a 5 in it, and A has a 1 in it, but it does not have the 5. So C is not contained inside of A. C is not a subset of A, so that's a false statement. And the reverse would also be false. A is also not a subset of C, because A has some things in it, the 2 and the 3, that don't happen to appear inside of C. The last one, sort of a funny one. A is a subset of itself. A is a subset of A. This is actually going to turn out to be a true statement, because if we think about it, if we look at everything that's inside of A and ask ourselves, are those things inside of A? The answer is definitely yes. A has a 1, 2, and a 3 in it. So if I say now, does A have a 1, 2, and a 3 inside of it? The answer is for sure yes. There's a couple of other things that we want to throw in, and some of it is a new concept and new notation, and this is the idea of an empty set. So far, I've only talked about sets as having things inside them, but a set could maybe have nothing inside of it. And if a set doesn't have any elements, you would call that the empty set. There's a couple of different notations you can use. One of them is using the curly bracket notation. So drawing two curly brackets with nothing inside, that shows that you've got an empty set. The other one looks sort of like the number 0, but we have to be very careful. This is not the number 0. It looks like a 0 with a slash through it. So when I'm saying that the empty set, it is not a number. That's just a symbol that I use to refer to the empty set. It's a set that has nothing in it, so 0 with a slash through it means empty set. So how would we get a set that has nothing in it? Well, by defining it as something that's impossible. So if I said that A was all the real numbers which are positive and negative at the same time, you would say there aren't any numbers that are positive and also negative. You could have a number that's positive, you could have a number that's negative, you could have zero that's neither of the two, but nobody is positive and also negative, so there's nothing inside of A. You could say A is the empty set. Or if we said, let's make a set of all the Canadian cities that are located inside of Africa, I would say there aren't any Canadian cities located inside of Africa. This is a set that has zero elements inside of it, so I would say this set is also the empty set. One little property, now that we've talked about the empty set, we can talk about a special property for subsets. And this is true for any set that we might be thinking about. The first property we've already thought about, that for any set A, it's always a subset of itself. And that's because if we were to look at the set A and say, what are the things inside of it, and then ask ourselves, are those elements inside of A? The answer would be yes, for sure. Everything that is inside of A is also inside of A. But there's another statement that we could also say, which is that the empty set is always a subset of any other set. And that's because if you ask yourself what's inside the empty set, well, there isn't anything. So is there anything inside the empty set that doesn't happen to be inside of A? Well, no. This is one of those statements that's sort of true in a sort of vacuous sense. There isn't anything inside the empty set, so yes, technically the empty set is contained inside of A. So what that means for us is if we had a question where I needed to list subsets, there are the two extremes. For a set A, there's the biggest possible subset, which is the one that's just set A itself. It contains everything. And then there'd be the smallest possible subset, the one with zero elements, the empty set. All right, let's do one more example. I have a set A, and it's got 4 elements inside of it, and what I'd like to do is to list all of the subsets of A. And so I think what I'm going to try to do here is to be a little bit methodical. I'm noticing that A has 4 things inside of it, so if I'm thinking about subsets, you could have subsets with 0 elements, and there's only one subset with no element inside of it, and that would be the empty set. You could have a subset that has 1 element inside of it, and we could find that there's actually 4 of them. You could have the set that just contains A, the set that just contains B, the set that just contains C, and the set that just contains D. So it looks like there's 4 subsets where there's only 1 element. You could have a subset with 2 elements. And again, when I'm listing these, remember, I'm listing subsets, and the order that I list the elements inside those subsets doesn't matter. So one subset might be A and B, but I won't also list B and A because that's the same thing. So for elements, 2 element subsets, you could have an A and a B, maybe an A and a C, maybe an A and a D, or perhaps a B and a C, a B and a D, or perhaps a C and a D. Okay, so those are 2 element subsets. Next one up, 3 element subsets. A little bit harder to think about, but there's still quite a few options to consider. There would be, you could maybe have an A and a B and a C. Or maybe you have an A and a B and a D. Or maybe an A and a C and a D. And maybe a B and a C and a D. And it turns out there's only 4 of those. At last one, the biggest one that you could have, the subset that contains all 4 elements, well, that would just be our original set A itself. So I could just write capital A. Or if I didn't want to do that, I could list A, B, C, D as a set. Either way, same thing. One thing we're going to talk about a little bit later on is the counting side of things. So if we were adding up, how many different subsets do we have in total? We've got 1 plus 4 plus 6 plus 4 plus 1 more. There are 16 subsets in total. And we might ask ourselves, could we have figured out how many subsets we were going to have before we listed everything? And the answer will be yes. And it's going to take some counting techniques to get there, but we are going to come back and talk about these things a little bit later on.